Hello everyone. In the last session, we briefly discussed about finite element method and we learned about certain terms which are very essential in finite element method, which are nodes, elements, and degrees of freedom. Now today we move into second chapter, which is on solutions of linear equations. What are linear equations? As you might already know, that the equations such as this one, which varies linearly with a certain slope and certain initial value, are known as linear equations. Now the linear equations may depend upon many variables, which may be x1, x2, x3 to xn, where you can have a1 x1, a2 x2, a3 x3, an xn, and you can have a constant b. These kinds of equations occur pretty often in our life. For example, let's say we bought a new motorbike for Rs 600,000. For the insurance, per month you pay, suppose say Rs 5,000, and per month in fuel you pay Rs 10,000, and every 6 months or so you pay Rs 6,000. This is your initial price, that's your insurance, and this is your fuel. We convert this to per month, so it will be Rs 1,000. If you want to find out how much will be the total cost for your motorbike if you have it for 2 years, let's say 2 years. Now if you look into the variables, now this will be a constant that you paid initially, which will be the y-intercept, and then these terms will have a single variable t, which is time in months. So you can form equation like total cost will be equals to, you can add these up, and this function depends upon time. Now here you can plug in 2 years, that will be 24 months. This will be your total cost of owning a motorcycle for 2 years. Now you can have other variables as well. Let's say what you do is you rent your motorcycle to Tutel or Uber, and you charge them per kilometer of distance that he has traveled. So let's say initially if the mileage was 90,000 kilometers and you charge him at a rate of Rs 50 per kilometer, so this will be your earning here. And then if we include this distance s as distance as a variable, then your equation will be modified into, where s is the distance the guy who has rented your vehicle has traveled. So in here we have two variables, t and s. Therefore linear equations will have a generic form of something like this. So you can have a lot of combinations. For example, if you have n number of vehicles that you rent or that you have bought, so this can be for your motorcycle, this can be for your car, this can be for your truck, and so on. So there can be many equations like this. and then you may have to solve them. In FEM, we generally write these equations in matrix form. We try to solve them in matrix form. So matrix is the basic here. So when you write this in matrix form, you'll get is this equation can be represented in matrix form like this. So that's A matrix X vector equals to B vector, where you have to solve for X vector here. You have to find this. Now there can be many solutions to it. There can be one single solution. For example, if you have two linear equations, which when you plot in your XY graph, they may be something like this. First equation may be like this, second equation may be like this. So they will only have one solution like this. So these are known as equations having unique solutions. So this is unique. They only have one solution. And for other cases, like when you have two equations which are parallel to each other, then they will never intersect, which means there will be no solution. And then you can have two equations like this which overlap each other. So that's the first one, and then you also have the second one going on top of it, which means every point in the black line will be coincident with the point in the green line. So they will have infinite solution. The way to solve this is X vector will be equal to, if you take this matrix on the right side, it will be A inverse B vector. That's how you solve it. Now there are many solution techniques to solve them. The first technique we're going to learn is the Gaussian elimination method. In this method, what we do is, if you have a equation like this and you want to solve for your x values, then what we have to do is we have to use some mathematical properties of matrices and convert this matrix here into this form. So when you apply different mathematical properties of rows and columns, you'll end up with something like this. So you can easily solve for x3 first, equals to c3 by k33. And once you know x3, you can open the second row. Now for this one, since you know the value of x3 from this equation here, you can substitute it here to obtain your x2. So x2 will be equal to, similarly, once you know x2, you can solve for your x1. So your x1 will be something like, now you have solved your problem here. You can get your x1, x2 and x3. So this is one of the methods. Let's look at an example of this one. Let's say we have this equation and we have to solve it using Gaussian elimination method. So the first step is to form your matrix equation like A matrix will be equal to X vector will be equal to V vector will be equal to, you actually don't have to write it this way, you can directly write your equation like, now let's try to solve this. Now the first step is to make this one 0. To do this, we have to either add or subtract these rows. Let's say this is first row, second row, third row. So to get this, we have to perform some mathematical formulations. We can do two operations. You can either do some manipulation in R3 or R2, keeping R1 same, or you can do manipulation of R1 and R2, keeping R3 same. So first we're going to try to make this one 0. What we can do is that if you look in R2, so our new R2 can be R2 minus 2R1. So when you subtract twice of this row from this row, then it will be 2 minus 2, then you will get 0 here. And similarly, your new R3 can be R 3 minus 4R1. So here we have kept R1 the same. Then what you'll have here is, here also you have to do the same. So here you get 10. Here you get 15 minus twice of this, you get minus 5. And then here 6 minus 4 times of this, 40. So that is minus 34. Again, let's make this one 0 now. To make this one 0, we have to subtract this one because we want to retain our 0 here. So we have to do manipulation in R2. So what we do is, your new R3 equal to R3 minus, let's say we have to multiply this by 6 by 5 R2. Therefore, our new matrix will be x vector equal to 10 minus 5, and here you'll have minus 34 minus 6, that will be minus 28. Now you have your equation. Now you want to solve it. So here we can write minus 7. So this is x1, x2, x3. So we can write minus 7x3 equals to minus 28. Therefore x3 equals to 4. That's your first value. And the other one will be 5x2 minus 5 x3 equals to minus 5. Now you can put here this value, that's your 4, and then you'll get your x2, that will be equals to 3. And again x1 will be equals to 1. Therefore your x vector will be equal to 1, 3 and 4. So that's your solution. Now there is another method which is known as Gauss-Jordan method. This method is similar to Gauss Elimination Method, but here your final A matrix will be of this form: x1, x2, x3 equal to c1, c2, c3. So here you can directly solve your equations. So x3 will be equal to c3 by k3. x2 will be equal to, and your x1 will be equals to c1 by k1. You can try solving the same problem and finally obtain this kind of matrix here. So let's try it. So you can start from here. So our target now is to make this one 0. Now to make this one 0, what you can do is, so after this what you'll get is, now we have to make this one and this one 0. To do this, what to do here is, now you can solve this easily. So you'll get x3 equals to 4, x2 equals to 3, and x1 equals to 1, which is the solution that we obtained earlier. Here 1, 3, 4, 1, 3, 4. Now this is known as Gauss-Jordan method. Now we move into conjugate gradient method. Conjugate gradient method is one of the numerical methods to solve linear equations iteratively. Gradient means slope. So these methods use slope to solve the problems. Generally what you do is, if you have an equation like this, let's say fx equals to some equation, then to find the minimum or the maximum value of fx, what you do is find the derivative and equate that to 0. We check this condition and we also check its second derivative and see if it's greater than 0 or less than 0. If these conditions satisfy, then we find minimum or maximum. Let's say your fx is this, and when you do a derivative and reach here, then the slope of this line will be parallel to x-axis. This will give you the minimum value, and in this range it will be also parallel to x-axis, and this will give you your maximum value. Now for conditions like this, where there are no constraints, for example, your problem might say that you have to solve it such that x lies between a and b. If this be a and this be b, then you have found your solution. And in such cases where these are not given, then your x can vary from minus infinity to infinity. Now these kinds of problems are known as unconstrained problems because your solution can lie anywhere here. Now these gradient methods make use of these derivatives to minimize or maximize certain equations. The gradient of fx is generally denoted by gradient means slope. Now we have a function fx and we want to solve it using the slopes or the gradients. Let's say that your solution is in this space. Your solution of the function lies here somewhere. So this is your solution, but this is not a direct method to solve it, so we have to do it iteratively. Let's say we assume our initial value of x somewhere here. Now within this equation we have to reach here. Now to reach here directly, we have to know the path. But I don't know. That's why what I do is, first we find derivative of the function at this point here and move into this direction like this and go to a certain point here, and then we find another slope and then maybe move into this direction and to a point here, and then we find slope of this point and then move in this direction here, and then find slope here, move in this direction here, and then finally we may move in this direction and reach to our solution. Since we don't know this path, we have to start at a point x1 and then move to x2, then x3, then x4, x5, and then reach our solution x6. So it took us 1, 2, 3, 4, 5 steps or 5 iterations to reach to our exact solution. This is how the gradient method works. So if the slope of this line here is m1 and this length here is alpha 1, then your x2 will be equal to x1 plus alpha 1 m1. We know x1, which we can assume x1 to be a certain value like say 0, and we will know m1, which will be derivative of our function at x equals to 0, generally negative, which will be equals to m1, but we don't know alpha 1. So we have to find alpha 1. Alpha 1 is kind of like your step size. We want to know how far we want to move in this direction so we can reach here faster. So in numerical methods, to find alpha 1, you can use Newton-Raphson method or bisection method and so on, and there are also analytical methods. And here we will directly use analytical method to find the value of alpha 1. If I write fx2 equals to function of x1 plus alpha 1 m1, then I can use Taylor series to open this. I believe you have studied Taylor series in your previous years. This will generally be in matrix form. What to do is we can write here f of x1 plus gradient of x1 alpha 1 m1 plus half of our second derivative. For second derivative we write transpose, and then we'll have a matrix here, A matrix at x1, and here this is how write derivatives in matrix form. This means second derivative, and we'll have a matrix here, A matrix. Now this matrix is known as Hessian matrix, and then when we do a derivative of this with respect to alpha 1, then equal that to 0. Now this will give us our step length alpha 1, which we require. The region we are finding derivative of function f of x2 with respect to alpha 1 is that we want to find the minimum length we have to move. This will be 0 because there is no alpha 1 term here. Now this will be plus here, which will be equal to 0. Now when you solve it, you'll get your alpha 1, which will be equal to minus. So there you have it. Now you have your alpha as well. This is your step length. Therefore, you can have your second point now, which is x2, which will be equal to x1 plus alpha 1 m1. In the next step, you will form x3, which will be equal to x2 plus alpha 2 m2, where you have to repeat the same procedure here to find your alpha 2 m2. and then you have to keep checking if the gradient is 0. If your alpha is 0 somewhere in the line, then you have to stop, and you have to keep checking your slope. If your slope at n is not 0, then you have to move into the next step where you will find x n plus 1. Otherwise, if your equals to 0, then you will have your solution as x n minus 1. We'll see this when you do an example. This kind of procedure is known as Steepest Gradient Method. The major problem with Steepest Gradient Method is that it generally takes a lot of iterations to solve a problem. As such, Conjugate Gradient Method came into picture. Here, the Conjugate Gradient Method helps to reduce the number of iterations to solve the problem. Let's take the same example that we took here. If this point was our required solution, what to do here is, if you take this one as initial guess, then we get a slope like this, and then another slope will be perpendicular to the first slope, and then we'll reach a point here. From here we'll reach a point here, and then from here we will reach another point, and then from here like this, which will also be 90 degree, to a point here, and then from here to here. We define a specific path to our iteration. This drastically reduces the number of steps. These slopes are not directly perpendicular or conjugate as you see here, but they are conjugate with respect to a certain matrix which is known as the Hessian matrix A, which is A here. So what will happen here is that we have to find M2, which is our next slope, this one. M1 and M2 are conjugate with respect to Hessian matrix. Now in the conjugate gradient method, what we assume is our M2 is linearly varying with respect to M1 as minus gradient of F2 plus beta 2 M1. Now we can substitute this here and then solve it. The result will be something like this. We'll get beta 2 will be equals to, similarly your beta I will be equal to, therefore you can obtain your M2, so your x3 here would be equal to M2. Now your M2 will be this one here, and then you can repeat your procedure again and again and again until you have alpha I equals to 0. Now in conjugate gradient method, the number of steps that are required or the number of iterations to solve a problem depend upon the number of variables which are known as decision variables. For example, for a problem like this one, and we have two variables t and s, then the number of steps that the conjugate gradient method will take will be 2. Similarly, when you have an equation like this, y equals to, then you can see here that there are x1, x2, x3 and x4. So there are 4 variables. Therefore, the maximum number of steps to solve this problem will be equal to 4. Now this is one of the advantages of conjugate gradient method. This method is also known as Fletcher-Revie's method. Now let's look at an example. Example will make everything clear. Let's say you are given 3 equations to solve. What I have to find first is the gradient of these functions. So the gradient f will be equal to derivative of function 1 with respect to x1, and then here derivative of function 2 with respect to x2, and derivative of function 3 with respect to x3. Now this will be equal to, if we do a derivative here, 3 x1 plus x3 minus 1. This one will be equal to minus x2 plus 3 x3 plus 12. And the third one here, with respect to x3, you get x1 plus 3x2 minus 2. Now this is your gradient, and then you have to find your Hessian matrix, which is given by this equation. Now this will be your A matrix. Now let's find our A matrix, which will be equal to we have to find derivative of this one 2 times with respect to x1. So this will give us 3. Here we do it first with x2, which is 0, and then this one with respect to x3 will give us x1, and the respect to x1 will give us 1. Again, this one with respect to x1 first will give us 0, and for this one with respect to x2 2 times will give us minus 1, and then for this one x3 goes x2 will give us 3x2, and then this will be equal to 3. Here first we have to find derivative with respect to x1, which will be x3, and then with x3 it will be 1. Here first with x2 this will give us 3x3, and then with respect to x3 will give us 3, and here this one with respect to x3 2 times will give us 0. This is your Hessian matrix. This is your gradient vector. In your examination, similar type of problem will be given to you in form of ax equals to b. So you'll be given to solve this problem like this. Here this one will be, when you take this one to the right side, it will be 1 minus 12 and 2. So in your examination, you will directly be given this equation to solve. We take this one as our Hessian matrix. This is our variables which we have to solve, and this one can be taken as b vector. So we start from here. So step 1. As you can see here that there are 3 variables, so the maximum number of iterations to solve this problem will be equal to 3. Here the exact solution lies somewhere here, and therefore we have to assume a point somewhere here. Let's say this is our first point. We have assumed x1 vector as 0, 0, 0. Then what we have to find here is we have to find our gradient at 0, 0, 0. To find the gradient at 0, 0, 0, see the equation we have derived here. We use this equation. So when you substitute 0, 0, 0 here, what do you get? You get minus 1 plus 12 and minus 2 here, right? Your m1 will be equal to negative of gradient of f1. We have to substitute 0, 0, 0 in here to obtain our gradients. Now this vector, as you can see here, equals to negative of b vector in your equation. So this one will be equal to negative of b1 b vector. So this one will be equal to, now this is our m1. Step 2 is to find our step. Our step is alpha 1, which will be equal to, so this is our alpha 1, so we write here, and this will equal to minus 0.5302. And the third step is to find x2, which will be equal to, this means that we started here and we have reached another point somewhere here, x2, using alpha 1 m1. Now we have to find another point which will be equal to x3, where we have to use alpha 2 m2 and beta 2. Let's find this point. Our m2 for this case equals to this one here, will be equal to negative of, now at that point at x1 y1 y2 we have to put these values here and obtain our values. If you are not given these equations here, the equation to find your gradient will be equal to then you have to find your beta 2 which will be equal to 1.97. Therefore your M2 will be equal to, now again, alpha 2 would be, I forgot to mention here about alpha 2. To find alpha 2, this will be equal to, these are all vectors. So in the first case, what we did here was we wrote M2 because we assumed the initial point to be 0, 0, 0. Therefore, this derivative here turns out to be equal to M1. But here, this doesn't happen because we're assuming our initial point to be x1 rather than 0, 0, 0. Therefore, this and this will vary. For this case, alpha 2 will be equal to this matrix transpose of itself, which will be equal to same as this one here, and then divided by, now this will be our alpha 2, our x3. Now this is our second iteration where we have reached here. Now there should be one more step left that will lead us to this point here. For this, similarly, we have to find out what is our alpha 3, M3, and beta 3. By doing so, you reach your x4 as, now this should be your solution, and then when you want to find your this value here for your fourth one should be nearly equals to 0, and that's when you stop. So this is how you solve this problem. I'll try to do this in Excel now. So what I've done here is I have also attached an Excel sheet in the description where I have solved this problem. You can check your equations. You can put values of other numerical problems as well to see if they match or not. This is it for today. Thank you for watching this video. Hope you like this session. In the next session, we'll look into chapter 3, in which we'll talk about elasticity in solids. If you have any questions regarding this session, you can comment below or send me an email in the description as shown. Please share, comment, and subscribe to this channel. See you next time. Thank you.